Hello. I wanted to do another video. I no longer have the light board, and actually the pins weren't quite working for me, so I'm trying this out. You can kind of let me know whether or not this is working. But in this case, I wanted to introduce a slightly more complex model than the random effects model. And in this case, we're going to work on what's known as the means as outcomes model. Now, in the means as outcomes model, again, we're going to assume that we do have nested data, but the reason we're calling it means as outcomes is the actual variables that we have that are covariates are at level 2, and we have no variables at level 1. So in the example that I'm going to use, again, we're going to have my nested data. In this case, we're still going to have my schools, and we're going to have students that are nested within schools. And the variable that I'm going to focus on as a dependent variable is going to be math achievement. So I'll just have my little math achievement sitting here, and that will be for the ith student nested within the jth school. Now, in addition to having math achievement as my dependent variable, we're going to assume that all the independent variables that we have are at the school level. Now, if I'm using the example that's originally from Rodenbush and Breich, then we might have something like sector. So this could be a dummy variable that's indicating whether or not the school is public or Catholic in their original data set, but we could also think of it as just a dummy variable to where it's 0 for public schools, 1 for private schools. Now, because that's at the school level, there's only going to be a J, meaning there is a single variable for every single school, but any student from the same school will have the same value. So that's why we do not have the I for the sector variable. Now, in this particular case, we could have other school level variables. For example, we could have things like school size, or we could have average socioeconomic status for that school. Now, the actual question that we're asking is, do we see that math achievement is different between public and private schools? So now what we want to do is move to the actual modeling. Now I'm going to switch from my notation just to a generic notation so that we can think of how this would work generically or generally, to where now I have my dependent variable y sub ij. And at level 1, whenever I'm modeling a y sub ij, we say, well, how are we trying to predict it? And in this case, there are no independent variables at level 1. So we're going to start with a beta 0j in a similar way that we did with the random effects ANOVA. So this is now modeling the average dependent variable for the jth school. In my example, if I used math achievement, we would say math achievement for the ith student that's nested within the jth school is equal to the school average math achievement, which we're now calling beta 0j. But we still want to allow for the possibility that any given student has a different math achievement from what's equal to that school average. And so we have r sub ij describing the extent to which the ith student that's nested within the jth school has a value of math achievement that's different from the school average. Now at level 2, we take the coefficients. And in this case, the coefficient that we have, or the only coefficient that we have, is beta 0j. Now just as a reminder, we said that beta 0j is the average of my dependent variable for the jth school. So in this case, it would be average math achievement. Now we're going to model that at level 2. We're going to start with an intercept, gamma 0, 0. Now in this case, the very first subscript, the 0, indicates what it is that we're modeling. So later on, we'll see that maybe we have a slope coefficient. Well, instead of a 0, we might have a 1. Here, it's just indicating that we're modeling the intercept. This second 0 indicates the position. So it's indicating that that gamma is actually the intercept. So we have gamma 0, 0. Now, in addition to gamma 0, 0, because we're interested in whether or not sector, so whether or not a school is public versus private, actually predicts math achievement, then we're going to also have a gamma 0, 1. Again, the first one indicating that we're modeling the intercept, the 1 indicating that this gamma corresponds to the first slope. And now if I use the notation from Rodenbush and Breich, I will use a W for all level 2 variables. So there's only a J subscript because we're now at the school level. Now in this case, that WJ would indicate sector, a dummy variable of whether or not it's public versus private. But W could also be any other covariate like school size or anything along those lines. Now it's entirely possible that above and beyond what W can explain, schools are a little different, meaning we want to allow any given school to be different from what we predict. And so we include a U sub 0j. So now we have two different error terms. We have my level 1 error term describing the extent to which the ith person's math achievement is different from the jth school average. And we would assume that that's normally distributed with mean 0 and a particular variance sigma squared. But we also have a U sub 0j describing the extent to which a school average is different from what would be predicted based on the school level independent variables. Now my U sub 0j is assumed to be normally distributed with a mean 0 and a tau 0, 0. And so ultimately, whenever we look at this, the reason it's referred to as means as outcomes is because whenever we look at level 2, this is ultimately trying to predict the mean of the dependent variable. But the advantage of my HLM model is prior to that, we are dealing with the fact that we actually have variability around that average that we can now account for. Thank you.